just going to say we're sponsoring.
Can y'all hear me? I can really talk loud. Can you hear me now?
Yes.
Okay. I don't care. Welcome to the Enrichment Series, Committee Series. We do these presentations throughout the semester, both fall and spring. And you may use your cell phones for note-taking or whatever, and your laptops, and make sure they're on silent so they're not ringing or anything like that. So today we have a speaker, Lawrence Federley, and I'm going to introduce him and let him tell you a little bit about himself before he talks about climate change. Give him a round of applause.
Thank you. I hope you do the same at the end. Okay. In 1972, I earned my undergrad engineering degree and worked for many years in that capacity, which got me, I was electrical engineering. We developed industrial controls, electronic controls, from 1972. So for lots of years, over 30 years, I worked in the engineering capacity, and because of the industrial control connection, we got involved a lot with the major processing firms. So our products were sold to the big chemical processing firms, pulp and paper, metals processing, refineries, all of that sort of thing, pharmaceuticals. But one area that it exposed me to that's pertinent to this talk was the area of energy. And so we got involved with we had one project we did with Niagara Mohawk, which of course is hydroelectric, right? Can you all hear me from the back? Is this okay? Because I'm just going to kind of talk as loud as I can here. Anyway, but then a couple of others, Florida Power and Light, there was another one, Ohio Power. These were the days right after kind of a big problem was developing. And I know some of you, let me just get a poll here. How many of you heard Congressman Ingles's talk? Nobody heard his talk? Oh my gosh. Okay, then I'll give you his main reference, okay? His main reference, which I think is required reading, especially for y'all, for the younger crowd here, is called Merchants of Doubt. Merchants of Doubt. How many have seen the book? Get it. Okay. The reason is it tells the story of starting off back in those days. First of all, it started with problems with tobacco and cigarette companies and whether or not tobacco really was a carcinogen, whether it was addictive and all that kind of stuff. They fought that for 30 years by creating misinformation or doubt, merchants of doubt. So they said, we need more research. We need more research. We don't know for sure if it's happening. The kind of conversation you heard 15 years ago, 18 years ago, was climate change is always all regular cycles, natural cycles, has to do with nature, has nothing to do with mankind, and so don't sweat it. Okay? A guy named S. Fred Singer wrote a book called Unstoppable Global Warming. Okay? And he showed how in the last 900-year period cycles, going back past the last glacier period, they just rise and fall, rise and fall. It was all natural. And we were in a warming cycle, and that's true, we are. There is a natural part of the warming cycle going on. But they denied that we had any connection to making it more exacerbated. Then we got into 2005 to 2010, lots of studies, lots of reports, lots of scientists, and they began to say, gee, there is something to this, there's something going on, it is unusual, but we have nothing to do with it. Now, you'll hear Tilson, who as you know now is the new Secretary of State, came out of ExxonMobil and admitted in his annual meetings that there's something to it and we're involved and we're going to have to do something about it someday. Okay? That was the conversation. So let me pick it up from there, and I'll go on through the presentation of this. This is the result of about 11 years. I'll preface it with this. In 2005, having been many, many years before, my gray hair here, in 1961, probably before or about the time your parents were born, I had the privilege of visiting Glacial National Park. And Glacier National Park is northwestern Montana, big mountainous area, beautiful glacial area. I mean, it has 150 different known segments that are called glaciers, okay? That means the ice is moving, right? It's not just there, it's moving. I saw a picture of it, an aerial photo in 2005. A good 3/4 of the ice was gone. So it raised the question in my mind, is that only Glacier National Park, or maybe the northwestern United States, or Alaska, or whatever, or are there other places? Then I discovered it's happening in the Alps, the Alpine region. If you went to Austria or to Switzerland, the Jungfrau or the Eiger areas of Switzerland, those Alps, you will find also dramatic decline in the ice over there, okay? And we have data, ice data, that takes us back not only 10, 20,000 years, but we have data that can go back now over 6 to 7, maybe even 800,000 years from data called ice cores. There's also ocean sediments that help to date things. There's coral growths that help to date things and that kind of stuff. Fossil leaves. So there's at least 4 measures that correlate very well in dating. Now, and so we can trace these things and know that what's happening is absolutely unprecedented. It has never occurred in the last 800,000 years in the way it's happening now and in the rate that it's happening now. So let me continue with this. All right, this old chestnut has been around a long time, but actually this is an expanded version of it. When Dr. Keeling, who working with the Scripps Institute, the Scripps Laboratories, was asked back in the 1960s or late 1950s to set up a facility or use a facility they had in Wanaloa in the Hawaiian Islands and begin to measure the carbon dioxide content of the atmosphere. And so he generated this kind of a chart. As you can see now, it goes up to present time, and it's continuing on up. The little cycles, the little rises and falls, are annual. Okay? So they follow the cycles of foliage growth and then decay, foliage growth and decay, and all of that kind of thing. And so the smaller versions are annual. But look at the next slide. This is saying, yeah, CO2 has been going up dramatically. And if you look at the left corner over there, okay, 410 parts per million. You're going to see charts later on going back many hundreds of thousands of years that it has never been above 300. Okay? I'll say that. You can take that as a quote. It has never been above 300 parts per million. With all of the drivers that cause the glacial and interglacial periods and all of that. Okay, now we're over 410. We're actually heading, I think very soon we're going to see 450. In 1890, a scientist by the name of Svante Arrhenius, who you, if you guys have taken any chemistry, you would know him as the person who did the original research on acids and bases and solutions and all of that kind of stuff. And another one, Joseph Fourier, before him, had made predictions. Fourier was the one who gave us the science around heat transfer. Okay? And so 2 of those gave us predictions of what would happen. Svante did the one who was saying, what happened if it all went away? We'd have an ice age. Okay? So even though at the time it was less than 400 parts per million, less than 300 parts per million, if it went away, its heat absorbing characteristics, right, would cause the Earth to cool in such a way that we would literally have an ice age. So what would happen if it doubled? That was the other reverse conversation. Here's what's going on. The top chart is the amount of CO2 that's going into the atmosphere as a function of time, starting at the beginning of the Industrial Revolution and moving forward to 2015 at least. And this comes from the National Oceanic and Atmospheric Administration. I can name 4 other international organizations that have done similar studies. Okay. So the land use change, a lot of that has to do with the burning of the forest. Okay. And when you burn any fossil fuel, you get 2 products, 2 main products. You get some byproducts, but 2 main products, which is carbon dioxide and water. Okay. So all fossil fuels, when burned, produce carbon dioxide. The green part, the land sink underneath, and the atmosphere portions of it, the land sink and the ocean sink. Okay, oceans absorb gases. If they didn't, the fish would die. Right? They have to have dissolved oxygen in the oceans. Well, they have dissolved carbon dioxide. It forms and makes carbolic acid. So the more CO2 you put into the atmosphere or into the oceans, the more acidic it tends to become. That's a whole different set of problems. But there's the trends. There's what's going on with the fact that the CO2 really is going up. And it's easy to argue, it's so small, how could it have any appreciable effect? Okay? Well, I'll point out to you that that little bit of CO2, even at 250 to 280, which has been the range for thousands and thousands of years, that little bit of CO2 sustains all the foliage on the earth, right? Okay, so let's keep going here. One conjecture was, yeah, we put some CO2 in the atmosphere, but the volcanoes are doing it. Okay, it's just they do far more than we do. All right, look at this comment. It comes from the U.S. Geological Survey. Some of these will be U.S. references, but we have international references that are very similar. It says that the volcanoes generate about 200 million tons of carbon dioxide a year. Okay, but the automotive and industrial activity, this is annual, this is year-round, this is global, okay, produce some 24 billion tons. Okay, so that stuff coming from the volcanoes, maybe 1%. 99% of the increase in the CO2 is strictly us. All right, so what's happening and who says so? Well, this is a short list, but some of the notables, and I'll point out a few of the more principal names. NASA, for many years, you're going to get introduced a little further into this with a lady by the name of Parkinson. Her last name is Parkinson, Claire L. Parkinson. She's been in NASA Jet Propulsion Laboratory since 1978, and one of her principal jobs is to track the changes in ice. Okay, you're going to see her a little bit later in this program and some of the things she has. One of the references, I wrote her, emailed, was able to end up calling her and asking her if she had some things she could send me. Okay, I had no idea that I was going to get a box about this big with all kinds of peer-reviewed science literature, Science Magazine, Nature, Climate, all the major science journals. This is one of the books that she was a co-author in, Our Changing Planet, The View from Space. So she's one of those who track the satellite data of what's going on with the Earth according to the measurements from the satellite. Okay? Claire L. Parkinson, a name very, very worth knowing. But look at the rest of these, and look at the international content. There's the British Antarctic Survey, Copenhagen Project from Australia. They're the ones that do the ice cores in the Antarctic. Okay, one of 3 groups. We have some people down there who do that, and the Russians do as well. Okay, so when we talk about measured data, actually first source, on-site, extracted information, we're talking about stuff that is done internationally. All of these can be correlated internationally. National Snow and Ice Data Center, if you look at that one, they're basically an archive of data, but you can go to them and get vast quantities of data. University of East Anglia, has been at this process in England for decades. The World Meteorological Association, one of the naysayers, I won't mention the names, but I give it to you, but anyway. The American Meteorological Association, one of the people who got prominent in saying it ain't happening, okay, his last name was Easterbrook. His initials were, never mind. Anyway, he was very prominent, American Meteorological Association, lived out west, claimed it wasn't happening, but when he actually gave a report to the Senate Energy Committee or whatever, and told them it wasn't happening, but he somehow left out all the changes that had taken place in the glacier, and he was from the West Coast. He was from California. And you think, well, Dr. Easter, you would have known that, okay? Why'd you leave that out? Right. So we find this again, it's a worldwide set of data. I'll point out one others. People talk about the IPCC and the reports they generate and so forth, okay? But I don't know very many people. I've been on with a number of the talk show hosts in the States anyway. This is the synthesis report from this is 2015. This is the IPCC reports, okay? So I said, given all the spare time I have, not. I will get these things and find a way to read them, okay? So I've had these now for about 6 months, and I've read through most of the material and the charts and so forth, okay? Their reports goes back to peer-reviewed first source science. That's very difficult. There is no better source. If you're talking about anything going on in science, there's no better source than peer-reviewed first source major journals, okay? That's where it all gets published. Doesn't mean they're always right, by any means, okay? But it does mean that they're the ones that have the best knowledge for the time, okay? So let's go on here. That's who says it is. That's probably 20% of who says it is. Okay, well, climate change, we say, is well known. I'm going to try this. I hope this works, because some of what I want to show you is out on the net. Where's the picture?
It's simple. It's basic physics and chemistry. It's physics and chemistry that we have known since the 19th century. Carbon dioxide is a greenhouse gas. That means that it's relatively transparent to visible light, but relatively opaque.
Technical glitch here. I'll tell you what we can do with the audio. We'll just go with the audio.
Making it simpler, light comes in, heat gets trapped. So if you put more carbon dioxide in the atmosphere, more heat gets trapped. And sooner or later, it has to warm up. That's basic physics, and there isn't really any other possibility.
I think what we don't realise is that the history of climate change is a very long one. History of climate science. It started with Joseph Fourier back in the 1820s.
Did you hear that?
Despite what you might have heard, this is not new in controversial science. We've known about the greenhouse effect for nearly 2 centuries. Joseph Fourier, the scientist who's well known for
This one is Michael
the
Mann.
mathematical technique known as the Fourier series. He is the same scientist who produced the law of heat convection. He's the guy behind the law that governs how heat moves through substances. He understood that there was a greenhouse effect.
It's all just basic science, it's physics and chemistry. And the key thing to know is that this isn't some
This is University of British
It
Columbia.
wasn't cooked up a few years ago. It's rooted in the
And then
basics
Simon
of physics
Donner,
and
Dr.
chemistry.
Donner.
Experiments on this started 200 years ago. So yeah, you might see some headline that questions some aspect of it in the news, tomorrow. But that can't affect the core, because the core is so grounded in what we know at this point.
that you'd have to tear up most physics and chemistry textbooks for us to be wrong.
So the next person.
I'm going to go forward here just a little bit to
Because the rest
this
of physics
fellow.
would be false.
In the late 1890s, we have Swedish Professor Svante Arrhenius, who is the next person to start investigating.
The planets would fall out of the sky because the rest of physics would be false.
In the late 1890s, we have Swedish Professor Svante Arrhenius.
I apologize for not being able to see the picture here. I don't know why that is. But I want to give just one more out of this set.
What the globe is doing and location years.
The first thing about climate warming
Professor
is
Eric
that the physical
Ringo.
basis we've known it
Oh,
for
we close to
centuries.
30
This
years,
is nothing
and
new
NASA did,
in
now he's got his own
science and climate
organization.
change today. You bring more CO2, more greenhouse gases in the atmosphere, it warms it up. It's undisputable.
The rate of emissions is thought to be far too slow to affect global temperatures back in the late 1800s, but by the start of the 20th century, the rate of emissions had gone up an awful lot, and so we've begun to realise that perhaps the rate of
This ain't the way it works at home. I have no idea what's going on here. Hold on, bear with me just a second. I actually tried to time this to 45 minutes. I may avoid using some of those and just speak from it rather than do that over again. Okay, we're back. All right. Again, what got me started was glacial activity, okay? It just raised my curiosity. With the engineering background, I taught, after I left the engineering career, I taught physics, chemistry, and math at various sites. Here I teach math for Tri-County, okay? And, but that background, the engineering background, the science background, gave me the opportunity, or at least let's say the skill base, the knowledge base, to do the research. For years I've been asking my own students, here's a subject, go do the research, and then critiquing their work. And I thought, well, if I can ask them to do it, I guess I can ask me to do it, all right? So what you're seeing is a result of some of that. Antarctica, let me point this out. This is the Amundsen Sea. Over there to the left is a peninsula, the Western Peninsula, which has lost almost all of its sea ice now. What's happening is the ocean water increasing a little bit in temperature was enough. Sea ice, as you know, melts or freezes about 25 degrees Fahrenheit, about 25 degrees Fahrenheit. And you raise that temperature just a little bit from what it was, and you're right at the melting point. And so that peninsula, the Amundsen Sea, the sea ice, what's called extent ice, has melted. When that happens, it's been blocking land-based glaciers from moving. Now the ocean-based, or the land-based glaciers in this area especially, but others around Antarctica, are happening 10 times faster now. The flow rate is 10 times faster. I'm going to try to move through some of this a bit more quickly. Well, we're okay. We're okay on time. All right, there's Antarctica, and you see these colored areas here, these shaded areas, okay? Those are areas that are now in motion, up to 10 times faster than they were merely 60 or 70 years ago, all right? Glacial changes, especially in Antarctica, they simply don't happen in decades. They happen in thousands of years, okay? Glacial changes are very, very, very slow. Up there on the peninsula, Larsen A and Larsen B are segments of that have lost all the sea ice, and that's now moving. We're going to see the same thing at Greenland, okay? And Antarctica is 90% of the world's fresh water. 90% of the world's fresh water. And as these glaciers, now what I don't want to do is I don't want to create a kind of a worst case scenario. Oh my gosh, next year it's going to be horrible. This is a fairly long-term trend by our life standards, that it's going to be 2100 before you're going to see really any kind of so-called catastrophic effects from climate change. We're already seeing a lot of it. It's measurable. The eastern coast of the United States ocean level, average ocean level, is up 8 inches already. Actually, it's up a foot. It's up a foot. On the west coast, it's more like about 6 inches. We have Greenland and Arctic and Antarctic and glacial ice that's adding it more. That'll equalize over time. Okay? So this is what's going on. There's the picture, okay? The deep sea, the circumpolar deep water, gets up underneath the ice shelf. That ice shelf, that's the extent ice, the ice that's over the ocean, that melts, and then that releases takes away the block, if you will, from the land-based ice that continues on down at a faster pace. All right, well, that's enough of that. Okay. Now notice this one. See the black lines going all the way throughout. Those are glacial areas. Those are independent glacial areas separated underneath by mountain ranges. Now we're talking about ice that's miles thick here. Okay? Antarctic ice has not changed in millennia, in many millennia. The ice core data that gives us a lot of information about what we know about the amount of CO2 in the atmosphere over a long time. When you do an ice core, you do hundreds and hundreds of feet, thousands of feet actually, taking out a section of ice, a cylinder of ice, if you will. It's about that big, around 10 to 12 inches around. And they extract that, and if you literally go back in time by taking slices out of that, and there's air bubbles trapped in that ice. And so you get the air that existed 10,000 years ago, or the air that existed 100,000 years ago. So we know exactly the content of the air over that long period of time. Right? Okay, that's the Larsen B areas. You can see here where the ice was out here before 1998, back to there, 1998, back to 2000. You can see it receding. That's the sea ice melting. That area, that's in Antarctic, and that segment in there, that open water segment in there, about 500 meters long, 1,500 feet or so long, or more, not very long ago, since the 60s, that was solid ice. Okay? So it's melted back.